So we are interested in checking CTL properties. So CTL, as you know, is a computation tree logic, a temporal logic that has a notion of branching time. So when we have a program that can have many different executions into the future, for instance, because of non-determinism or because of input, we can either talk about all those possible executions, or we can also existentially quantify over such executions. So in the red box on the slide here, you see the CTL fragment that we consider in this paper. So a formula is either an atomic proposition. We have negation, conjunction, and disjunction. And then for the temporal operators, they always come in two flavors, either with a universal quantifier, capital A, quantifying over all future executions from the current state onward, or with an existential quantifier, capital E, talking about the existence of one execution from now on. And so we have three such temporal operators. We have the X talking about the next state. So in all future executions, in the next state, phi holds. And here the same for existential. We have an until, which says that it's a strong until. So eventually in the future, the second phi here must hold. And until then, the first phi must hold. And we have a generally. So in all states, phi must hold. And the same here. So on the right-hand side, you see two examples. So for instance, here we express that in all executions, black must eventually hold, right? So we have something we don't care about, true until black eventually holds. And you see this holds in this execution here because no matter how you proceed from the starting state, you will always reach a black state in the future. On the right-hand side, I have an existential example. So blue until black must hold on at least one future execution, and it does on this one here. So you have blue, blue, and then eventually black. There are others on which it doesn't hold, but with the existential, that's fine. So that's the kind of logic, the kind of properties we would like to analyze. And our goal was to check those properties, and in particular to be able to infer sufficient preconditions that tell us for what input states a program satisfies such properties. Also, compared to earlier work in this space, a particular focus was on handling existential properties which were not fully supported by other work. So how do we do that? Let me first introduce a running example to give you an impression of what our technique does. So here I have a loop that iterates an arbitrary number of times. So rand is just a random, like a coin flip. And then I set x to 1, I increment y, and I set x back to 0. So you could, for instance, think of x being set to 1 as a log operation and it being set back to 0 as an unlog operation. And afterwards, I run into some infinite loop here. And imagine that our specification is that on all executions, we want eventually x to be 0. Okay? Then you see this will always hold if you enter the loop, right? So then you will always eventually see a value 0 again. But if the program never enters the loop, it might, well, skip this loop and then do nothing afterwards. And that shows you that this property only holds if x is 0 to begin with. So the precondition we would infer here is that x is 0 initially, and then the property holds. So let me show you how we do that. So we start with the program semantics, where we use a maximal trace semantics. So we look at all the finite and infinite traces of our program. In order to see how we do that, it's easier to go from a program text to a control flow graph. So this is how I will represent programs from now on. So it's the same program as before. We have the loop here, and then eventually we leave the loop and we go into this infinite loop here. And then we collect all the traces. Here are 4 of them. Of course, there are infinitely many. And you see, for instance, the first trace starts in a state where x and y are both 0. And then it does not enter the first loop. It jumps to program point 5 immediately, and so the value stays 0 until eternity. The third trace is one where the property doesn't hold. We start out with a state of 2 and 3, so the property doesn't hold initially. And then again, we jump immediately to place number 5, so we skip the entire first loop, and so the values won't change anymore, and x is never going to be 0. So what we do, based on this trace semantics, we define a special program semantics for a given CTL formula. So the idea is the following. For every state, we have let me say it differently. So we define a function that, given a particular CTL formula, tells you whether or not the formula holds in a particular state. So the way we do this is as follows. The function that we define is a partial function. If a state is in the domain of this partial function, that means the property, the CTL property holds. Moreover, the function yields an ordinal value, and we use the ordinal value as a ranking function. So if you have an until function, the ordinal value tells you how many more steps you need until this formula, the until formula, actually holds. So we need ordinals here to deal with unbounded non-determinism, but for the purpose of the talk, you could as well just think of natural numbers. Okay? So let me give you a concrete example. So here's our program again. So let's imagine we look at the property that we want always true until x equals 0. And let's see what the function that we define, that's the function here, gives us for the initial state. So this function would give us 0 if x is initially 0, right? Because then the property holds immediately, so it holds, so it's defined, and we need 0 steps until it holds. If x is not initially 0, the function is undefined, right? And that means that the property does not hold. And we have seen that it doesn't hold because the program might continue like this, and then x will never be 0. Similarly, if I look at the same property but with an existential quantifier, so there exists an execution on which x will eventually be 0, then my function at the program start here again gives me 0 if x is already 0, so then I'm good. And otherwise it gives me 3, because there exists an execution, namely the one that goes down here, in which after 3 steps, 1, 2, 3, x will actually be 0. Okay? So there are 2 aspects that are important here. The most important aspect is the function defined or not, so the domain of the function. The second aspect is this ranking function that we define this way for the until properties. And now we have a concrete semantics that gives us the precise characterization of whether our program satisfies a CTL property or not. And the goal is to define a static analysis that approximates that concrete function such that we can build a static analyzer. So here's how we do that. So as an abstract domain, we use piecewise defined ranking functions. That's a domain that has been developed earlier by Katharina Urban and Antoine Menet. There are a couple of references here. And so the idea is that we define an abstract semantics based on these piecewise defined ranking functions such that the concretization of that abstract, of those abstract values, give us these functions that map state to ordinals that we have seen on the previous slide. So the way we represent those piecewise defined ranking functions is through decision trees. So here I have an example, and here's the mathematical notation of the function that we define here. So that function is a constant 4 if x is greater or equal 4. That's this segment here. It's 7 minus x if x is less or equal 2. That's this segment here. And it's not defined between 2 and 4, so it's bottom there. And we define those via decision trees. So decision trees have interior nodes which are conditions, like x greater 4, x less than 2. To the left, you see the value of the function if the condition is true. So if x is greater or equal 4, the value is 4, as you can see here. And to the right, you see what's the case if the condition is false. So if x is not greater or equal 4, but less than or equal 2, then this is our function. And if it's also not less or equal 2, then it's bottom. You see we define the same kind of function as we do here. And the way we represent those is we use constraints of some numerical domains for the conditions. In our experiments, we use polyhedra for that. And we use affine functions for the leaves to give us the ranking functions. And now that we have this abstract domain, we can actually define our static analysis, which is a backwards analysis that infers these functions. And so if we have a more complex CTL formula, we do that by looking at each of the constituent formulas individually and then step by step building up the entire function. So let me show you how we do that. If I go back to my running example that I want in all executions x eventually to be 0, then I look first at the constituent formulas. So the primitive formula here is x equals 0. And then I go over my control flow graph and I define this function. And for an atomic proposition like x equals 0, that's super easy. So that's what we get. I hope you can see it here. So in any state like this state 4, if x is already 0, then the condition is true, and true in 0 steps. So that's why I have this gray dot here. I hope you can see that. And everywhere else, the function is undefined. because if x is not 0, then x equals 0 doesn't hold, right? And we represent something that doesn't hold by a partial function that is not defined on that state. So that function is only defined for x equals 0, and there it has the value 0.
Sorry, you said you started backwards.
Yeah.
So how do you start? With what formula?
So for the atomic propositions, this is the same everywhere. For every state, right? You just check, does the atomic proposition hold in that state? If so, you get this 1 point and the rest is undefined. And so there is not much backwards going on yet. It's going to happen when I introduce the until.
Right. I mean, you said you do a backwards iteration. So
Yeah.
you iterate some predicate transformer on sets of states.
Give me a second. On the next slide, you will see the backwards iteration. Ask again, please, if it's not clear then.
Set of states. I don't want to see the backwards iteration. What is the set of states?
This is initialization here of the backward.
So this thing here is a function, right, that for a particular state tells you whether the property holds or doesn't hold.
But how do you get it? I mean, you only get it when you look at forward semantics, right? You know that if you go forward, then from 3 to 4, then you get that x is 0. But I don't see how you get it from backwards.
So for the atomic propositions, I don't have to go either backward or forward, right? I just need to look at the condition here, and that gives me this function immediately.
So perhaps the question is why you started at 4.
Well, I could have started somewhere else. So
Okay.
how
So,
about here?
yeah.
Or,
Okay.
or maybe there.
Good. I think this was the question. Yeah.
Okay. So sorry if I did not understand the question. So for the atomic propositions, all of that doesn't really matter, right? It gets more interesting if we look at the whole formula. So for the atomic proposition, in all states, we have this property. If the atomic proposition already holds, we are there in 0 steps. Otherwise, it's undefined, okay? But now we need to go to the full property, so the same program as before, but now we really want it's always the case that we have true until x is equal to 0. And now our starting point is what we already know about the atomic proposition, right? That's information we already have. And now we can basically start at an arbitrary program point, or if the program is terminating at the end, and start iterating. So for instance, at this particular program point, that's what we already know from our x is equal to 0 analysis earlier. And now we propagate this. So if I go backwards here, then nothing's happening here. I reach a fixed point immediately, and then I can also propagate it backwards here. And then I get the same property because there's no statement being executed. And then I cannot continue here because there's a branch here, so I need to first figure out what's happening on the other branch. So I can start from another node. Let me start with node 4 here. Again, it doesn't really matter. And I can propagate this backwards. So this is what I got out of my x equals 0 analysis, and now I propagate it backwards, right? So my next statement is x gets 0, and that gives me this property, right? So if in state 3, x is already 0, then the property holds in 0 steps, and otherwise it will hold in 1 step. So it's a function that is defined everywhere. It gives me either 0 or 1, depending on the current value of x. And now I take this back further. So y, of course, doesn't affect my property here. So I just move the line 1 up because I need 2 steps until x is 0. Unless it's 0 already, then I still have the gray dot there. And then I have yet another assignment here. So I need 3 steps now to reach x equals 0, or it's 0 already. So now we are at this point where we need to join, right? And now the important thing is this here in my program is a non-deterministic choice, right? I could either enter this loop or I could go to the other loop. And I have a property that talks about all executions, and I want the eventually x equals 0 to hold on all of them. In that sense, intuitively, when you combine what you get from one edge here and what you get from the other edge, when you combine those, the combination needs to preserve the undefinedness, because undefinedness is the conservative choice. It says the property doesn't hold. And if there is one execution on which the property doesn't hold, then the universally quantified property, of course, doesn't hold. So when I combine those two, in a sense, wherever one of them is undefined, the undefinedness wins. And that gives me this result here, right? They agree on the value for x equals 0. It's 0. That's what you also see here. And otherwise, the undefinedness from here wins, and that's what you get. And now I can push this further around this edge, and you notice that I end up with the same graph that I had at the beginning, so I've already reached the fixed point, and this is the result of my analysis. And so from here, you can immediately read off the precondition that I showed you earlier. The property holds if x is equal to 0, and otherwise it doesn't hold. That's exactly what we saw up front. Okay, so far you've seen a simplified setting where we had non-deterministic choices here. So it becomes a bit more interesting when we look at conditional statements rather than non-deterministic choice. So let me introduce another example to illustrate that. So here in my example, I branch on x greater equals 0. In one case, I set y to 1. In the other case, I set y to 0. And my property is that on all executions, I want y to be 1 eventually. Okay? So now again, we can run the same kind of analysis. So at this program point, we will get this graph because I mean, in one step, no matter what x is, we will definitely reach a state where y is 1. So what I've done here is I project basically the state space which contains x and y only on the x-coordinate, just for the purpose of visualization. So I only look at the x here because the x determines my control flow, and so the y, in a sense, doesn't really matter. So no matter what the x is, after one step, y equals 1 will hold. Thank you. On the other branch, I get a function that is totally undefined, right? Because if I'm there, unless y is already 1, which I ignore here, no matter what x is, it's not going to be the case that y is eventually 1. Okay? And now again, we get to this point where we have our two results from the backwards analysis, and we need to combine it. But this time, it's a conditional statement and not a non-deterministic choice. And I told you earlier, if we have a universally quantified formula, whenever we come to this combination, the undefinedness wins, because we want to be sound, we want to be conservative. But that would be too conservative here, right? Because this thing is always undefined, but of course this only matters if the if condition is false. We need to take this condition into account somehow. So this is how we do that. So we represent this function as a decision tree, so it's just the function constant 1. We represent this one as a decision tree, so that's just the bottom. And now we take into account the condition of the if statement, which basically tells us that in this case, this entire gray area, so x less than 2, is irrelevant because we would not ever get there. And similarly, and we can represent that in a decision tree by saying if x is greater equal 2, then we get the 1 here. And otherwise, it doesn't matter, we will never get there. Okay? And similarly, in the other branch, we know that this branch only matters if x is less than 2, because otherwise we will not get into this branch. So I can represent that by saying if x is less than 2, then it's bottom, and otherwise that doesn't matter, I'll never get there. And now again, I have two functions that are non-overlapping, so I can just combine them very easily. And this is my result then. So what I get is if x is greater equal 2, I'll be there in 2 steps. Well, the 1 step from here, and then 1 more step for the if statement, so 2 steps. And otherwise, I'll get the bottom from here, and I know exactly what to expect. So things become, yeah.
So, and where do you capture the fact that, I don't know, if y can be 1 at the beginning?
I don't capture this here because otherwise I get like 2-dimensional graphs, okay. So of course so the analysis takes this into account, of course.
Okay.
Yeah. So let me make things a bit more interesting. So now it's the same program again, the same property again, but I make my my if condition a bit more complicated by saying x must be greater equal than 2, and also an even number. Now if we do the same steps again, this doesn't change, this doesn't change, this doesn't change, this doesn't change. All of that is the same. And now we again come to the point where we want to combine those two functions into one for the entire if statement. And now if we think about which portions of those functions are relevant, it's a bit more complicated. Because here, only the values greater equal 2 that are even matter, right? So we can represent those. And here, only those less or equal to and those that are odd matter. Okay, so we can represent those. But I told you earlier that what we do in those decision trees, we use a numerical abstract domain to represent the constraints. So if we assume for a moment that we don't have parity for our constraints, and we just have polyhedra, then this is something we cannot represent in the abstract domain. And so therefore, we need to approximate. And so what we do is we over-approximate those conditions. So this one would just get over-approximated to x greater equal 2. And this one would get over-approximated to just true. Okay? And now you have again the state where you need to merge. And again, you have a universally quantified formula. So whenever one of the functions is undefined, undefinedness wins because you want all future executions to satisfy the property. So this is what you get. You get a function that is undefined everywhere. So in the tree, you see the condition is true, and you always get bottom. And well, that's a sound solution. Of course, not a great solution, but a sound solution for this problem. So intuitively, what you can imagine is when we over-approximate this condition, we make the condition more true, right? We go closer towards true. So we make it more likely that we take the left-hand branch here, the 1 or the bottom, and less likely to take the nil branch. And since bottom wins, since we make it more likely that we take the bottom, we'll find bottom more often in the result, and that's a sound way of approximating things. So here's a little twist. So now I change my properties into an existential property. As I say, there exists an execution on which y will eventually be 1. And I also changed the program a little bit. I turned this into a disjunction instead of a conjunction to make my point clearer. So this is the same as before. So after this assignment here, we get this function. This is also the same as before, and also those conditions are the same. So now if I apply the same strategy that we've discussed before, I'll gray out the portions that are irrelevant, and I represent them in the decision tree. Same thing in the other branch, and I represent them. So now these are again conditions which I cannot represent in my abstract domain, so I over-approximate them. So this gives me true over here, and x less than 2 over there. And now I define the 2, but now I have to be careful. This time, it's an existential quantifier. That means if one of the two options is defined, the property holds, because there is then at least one way I can execute the program such that the property holds. Okay? And so since this one is always defined here, I'll get back a result that is always defined. Okay? And now what you see, this is clearly unsound, right? We have an implementation here that for some inputs never sets y to 1, and nevertheless, my analysis tells me it always does. So what I just showed you is unsound. The way of computing the if statement works for universally quantified formulas, but not for the existentially quantified formulas. Again, what's the intuition? The intuition is by over-approximating the conditions here, I make it more likely to take the left-hand branch. Okay? If the left-hand branch is defined, I'll take it, because for the existential quantifier, definedness wins, but taking the defined branch is not necessarily conservative, right? Because if you have an overlap, it would be conservative to say the formula doesn't hold than to claim that it does hold. So that's where the problem comes from. So what we have to do instead is the following. If I am at this point that I have a decision tree that I need to approximate, and I have an existentially quantified formula, I cannot over-approximate, I need to under-approximate the conditions. Okay, so I make them more false in a sense. So if I under-approximate this condition here, I get x greater equal 2. If I under-approximate this one, I get false. And now I can combine the two, again with the same idea. If it's an existential quantifier, definedness wins. And so this is what I get then. I get a function that is constant for values greater equal 2. And you see in that case, we will really always enter the then branch, and we will really always set y to 1. But it's undefined for the other values, because for those values, we might enter the else branch, and that would be unsound, so the formula doesn't hold there. So that's the important insight. When we have existential properties, we need to under-approximate the conditions. When we have universal properties, we can over-approximate them. So we proved soundness is the soundness result that you would expect. So a CTL formula phi holds for all traces of a program starting from an initial state sigma, if sigma is in the domain of our partial function, so we take the piecewise defined ranking function that I just explained, that we compute during the static analysis, and if we concretize that, then my start state must be defined for that function, so must be in the domain. And the proof, of course, is in the paper. So for the evaluation, we implemented this analysis in the function static analyzer. That's Katharina's tool that she developed for termination analysis and other things. It takes a C-like input language and is available as open source if you want to play with it. And we picked a couple of examples from the literature, from other tools, like Andreas's LTL analyzer, and from the SVComp competition. And for the implementation, we chose polyhedra for the constraints of our decision trees, and we chose affine functions and ordinals for the leaves. Again, ordinals are needed for unbounded non-determinism. And so we ran a couple of examples on this slide. You don't see all of them, because here I only show those examples where different tools that we evaluated show different results. So those examples where all the tools have the same outcome are not shown on the results. So what you see on the left is the conditions that we checked for those programs. On the very right, you see the analysis time, which is generally very fast, but the programs are also quite small, usually dozens of lines of code. And here you see the result. So green tick, of course, means we computed the right result. The red cross says that our analysis claims the property doesn't hold when in fact it does hold. So we have a couple of examples where the analysis is not precise enough, and that's in almost all cases, of course, due to widening. So we also compared this to two other analyzers for temporal logics, so to T2 and to the ultimate LTL automator. Let me explain what the notation here means. So the minus means that we could not run this example. In the case of T2, that is because it has a different input format, and we were not able to produce all examples in that input format. So there are a couple of examples we just didn't run there. And then there are a few examples where T2 worked well. So for instance, there are two examples here where T2 gave the right answer, but our tool didn't. But there were also a couple of examples where the property was either not supported at all in T2, so we got an error message that this is not possible, like in this case, or we just got the wrong answer. For the LTL automizer, that did very well in the comparison. So here the minus means that it's a CTL property that cannot be equivalently expressed in LTL, so we just couldn't run it. So you see those are the properties that contain existentials. But for those where we were able to express them in LTL, the LTL automizer checked all of them correctly. So it was just a perfect result there. Congratulations, Andreas. All right, so let me sum up. So we presented a theory for analyzing CTL properties using abstract interpretation. What we do is we infer sufficient preconditions. So if that precondition is false, the formula doesn't hold. If it's true, it holds for all input states, and otherwise it characterizes the input states for which the property runs. The analysis is implemented. The implementation is available if you are interested in trying it out. And in the future, we would like to apply our ideas also to LTL, but we haven't started that part yet. Thank you.
Questions?
Yeah, nice work. Couple of questions. First question. So you mentioned that you could also use infinite ordinals. Can you give me an example where you need infinite ordinals?
So what we need is if you have a non-deterministic choice which is unbounded, right? Then we need to express that we have kind of one step in addition to all this. So imagine you take non-deterministically a number and you iterate that many times.
Yeah.
Right? You basically need to say, I want the highest possible number that I could choose, and then plus one. So that takes you out of the natural numbers and into the ordinals.
Okay. And the second question is, do you have some sufficient condition that guarantees some completeness of your framework? So I mean, if some CTL formula is true, then your analysis is able to derive it.
Well, I think this would happen only if we can represent all the branching conditions in the program within the abstract domain for that we use in the decision trees. So as soon as we get into this abstraction business that I explained here, right, this business here, then we lose completeness.
And widening.
And widening, of course, yes. Yeah.
Okay, another question?
My question was on widening because in the previous papers it was a bit subtle. And it is the same widening that you use now?
Yeah, it's the exact same abstract domain that Katharina used in her previous work.
Yes, so this one is a bit, that's where the power is.
Yeah.
So there is this tool by Logozzo and Kuzo which infers necessary preconditions. So instead of expressing correctness, they express incorrectness, and so it's necessary. It's interesting to derive this. So can this framework be adapted so to make to make the other approximation, right? Right now you infer sufficient preconditions. No, but right now it makes an under approximation. Right? In a way it iterates WP and it makes an under approximation.
You negate and they do also under approximation. If you negate, they will do over approximation. I think if you take the negation of the formula, you will get a necessary condition for the formula to be
I don't think so, not if the formula is approximate.
Yeah.
Right? If the formula is approximate, conservative, then just by negating it, you don't necessarily get the necessary condition. So only if it was absolutely precise, that would work. I really think you need to infer the necessary condition kind of from the ground up. You cannot just take the result and flip it. So I would hope, but this is really just a hope, that by changing the way in which we do over and under approximation, we could get there, but I've not actually worked this out. So I don't have a definite answer on that.
Any more questions?
Yeah, so in your example, you showed how you treat EF, AF, right? So using a termination argument. So for AG, EG, you just negate the result and get sort of, so here you get either true or maybe. And then for AG, EG, you would have sort of the other way, false or maybe.
I'm not sure I understand
Okay, the question is, AG and EG, do you treat as negation of eventually?
No. No, there are different transformers for those properties.
Any more questions? Okay, let's thank the speaker again.
Thank you.